Now we will talk about the reserve estimation techniques, and this can be basically the main part of the whole course. There are so many techniques for reserve estimation, and before we go through them, so whatever we cover in this course so far is starting from type of well logs and how we interpret different type of well logs, and how we can use them to calculate different parameters like porosity, water saturation, shale volume, and so on. And now we are coming to how we sorry for that, and how we will use those parameters to calculate the reserve. As I said, there are so many techniques to calculate or to estimate the reserve, because if we said that we are calculating, so that means it's an accurate value, but we are just estimating whatever we have, or the amount of hydrocarbon that we might have in the reservoir. So we have the analogy technique, in which we are just correlating our reservoir to another reservoir that might have the same condition and the same parameters. So if we have another oil field or nearby oil field in which those two fields, they are sharing the same, let us say the same type of source rock, almost similar maturity level, TOC, total organic carbon, and kerogen type, same pressure, temperature, all those parameters, if same lithology, same structure, style, if there is similarity between those two oil fields or those two reservoirs, we can assume that maybe the reserve in this oil field can be similar to that one. The volumetric method, it is the one we are going to cover now. Material balance method, it's based on the fact that the amount of hydrocarbon or the hydrocarbon reserve is equal to the amount of hydrocarbon that has been produced plus the hydrocarbon which is still in the reservoir. So if we can calculate the amount of hydrocarbon in the reservoir, and we can the hydrocarbon that have been produced, so we can easily get the entire reserve. The production history using decline curve, and this is this technique is based on the assumption that the decline in production rate take place with time, and with that there is also a decline in the pressure of the reservoir. And using this technique, normally we can predict the performance of our reservoir in the future. There are different type of curves. It can be exponential, hyperbolic, and harmonic. Each and every curve has its own conditions and scenarios. Now let us come to the volumetric reservoir estimation. To better understand this technique, there are some terms that we have to go through. First term is original oil in place, or OOIP, and in some places you might find it STOIIP, which is stock tank oil initially in place, and this represents the amount of hydrocarbon that's in, or oil or gas in the reservoir at the initial condition, which is initial pressure, before production take place. The unit is stock tank barrels, and it's called stock tank oil initially in place. So it's simply the amount of hydrocarbon, or the amount of oil or gas in the reservoir in the initial conditions before production. So that's mean the reservoir is at its highest pressure value. So if, for example, we have set of data at different stages within the reservoir history, and we want to estimate the initial, or the original oil in place, or the stock tank oil initially in place, we will simply go for those which are related to the highest pressure value. Now the original gas in place is the same thing with it, just for the gas. So it's the amount of gas which is in the reservoir at the initial pressure before the production. It's called original gas in place, or gas initially in place. So it's OGIP or GIIP. We have another parameter which is oil in place, OIP, which is the amount of oil, or the estimated oil, including producible and non-producible oil, that is in content in the reservoir at some pressure other than the initial pressure after production may have commenced. So in this each one of these have an equation. So in this one we are just basically referring to this hydrocarbon, or this oil which is in the reservoir that we might be able to produce, or maybe not be able to produce at specific pressure, and this specific pressure is referring to specific time in the reservoir life. And this pressure is not the initial pressure, because if it's the initial pressure, now we will be talking about the oil, the original oil in place. But if we are calculating this amount of oil, or we are estimating the amount of oil at any pressure other than the initial pressure, we are talking about oil in place. Gas in place is the same thing. It's the estimated gas in the reservoir, which basically can be produced or non-produced at any specific, at some pressure other than the initial pressure. Now these are the equation for the volumetric calculation, this one for oil and this one for gas. As you can see, both equations are almost similar, there is only two difference between them. The first one is this constant, and this constant is basically to change, it convert from the area, because convert these values from area into barrels. The same thing here, this factor is changing it from area to cubic feet, which is the unit for the gas. Other than that, the second difference is the formation volume factor, which is this value. And in the next slide you will see how we can calculate this value, because this value is actually what is controlling if we are measuring the stock tank oil initially in place, or we are measuring the oil in place. If we change this factor from BOI to BO, that will shift it from stock to oil initially in place. Same thing for the gas. If we remove the initial parameters, so that will shift it from gas initially in place to gas in place. We'll see that in the next slide. Before that, we have the definition of the formation volume factor. In a simple way to explain it is that we need this factor because the amount of hydrocarbon, or the amount of oil or gas, or the volume of those oil and gas in the reservoir is not the same as its volume in the surface condition, because in the reservoir it's subjected to the high pressure and high temperature, which is going to cause a certain type of changes. When we change those condition of pressure and temperature for the reservoir, that will basically change the physical condition of those fluids and gas. For example, some of those changes that gases which are involved in the oil solution under high pressure, when we decrease the pressure by taking this hydrocarbon to the surface, those gases will be released, so we lose some of the mass of those solution, and thus the volume will also be decreased, because if those gases are in liquid phase under high pressure, when we release this pressure, so those gases will be transformed from the liquid into gas, and they will be released, so the volume will be decreased. The oil volume as well as a liquid will contract, because those fluids will be cooled since it was at high pressure and temperature, and when we reduce the temperature, so it will shrink and contract, and that is at a lower temperature. The same time, those fluids will expand because the pressure will decrease on the surface according to that one in the reservoirs. So those fluids will basically expand. Now the formation volume factor, we said that it's the one which is control or the one which is shift our equation from being in initial condition to other to the calculation in any other pressure or temperature or any other condition other than the initial condition. And in a simple definition for the formation volume factor is that it's the volume of n moles of liquid at reservoir condition to the volume of the n moles of the liquid at the surface condition. So it's the ratio between the volume of the n moles of specific liquid at reservoir condition to the same amount of this or same volume of this liquid at the surface condition. And the unit here is reservoir parallel to stock tank barrel in the surface, and at the reservoir it will be reservoir barrel. Now let's see how we can calculate the formation volume factor. So this is our equation, the one we have seen earlier is the factor that convert acre to and feet into barrels. The equation is equal to, so H is the area, which is the area of our reservoir in acres, and the H is the thickness of the pay zone, and we can get this one from the logs. Phi, of course you know that we can get it. I will not say which type of logs we can get this value from, and this value is representing the hydrocarbon saturation, which is equal to 1 minus the water saturation, and it's a fraction, so it doesn't have any unit. And the formation volume factor, which is reservoir barrel by stock tank barrel. So the basic assumption for calculation of the formation volume factor is using, and the basis for the assumption for calculation the formation factor for formation volume factor is using the ideal gas equation, which is NZRT divided by P, and this is the volume, and we know that the equation is NZRT divided by P, and this is in reservoir condition, and this is one in standard condition, according to the previous definition that we have given. So by manipulating those two equations, we can reach this one. This one n, the n will cancel n at standard condition, and we have Z, which is the gas deviation factor, and or it also known as gas compressibility factor, and it's basically defined the change in the behavior of the gas from the ideal gas. So the Z value for the ideal gas, which is in the standard condition, is equal to 1, while for in reservoir condition is not equal to 1. So now this one gone, this one gone, this one is equal to 1. We remain with this one. So we have this one is unknown, the temperature is unknown, the two temperature and the two pressure values. So we have in reservoir engineering that the temperature in standard condition is equal to 60 degrees Fahrenheit, and the pressure at standard condition is equal to 14.7, and by substituting those values, so now we have those two, we will only remain with Z, T and P, those three unknown values, and the rest is equal to this one. So this gives us the final equation for calculation a formation volume factor for gas. So what's happening here is that as I said, this equation or this value, it's the one which determines what we are calculating, if we are calculating in the initial condition or if we are calculating in any other condition. So if we are calculating in the initial condition, we will just substitute the pressure and temperature. The reservoir temperature is the same either in the initial or at any other stage, so that's another assumption. T will not change, Z will change, and P will change because the pressure at the initial condition is not as the same as the pressure after production take place. So we will always expect that the pressure will drop unless there is some other treatment that take place to build up the pressure of the formation, but in the normal case that the pressure will drop as the production take place. So if we are being asked to calculate the formation volume factor at the initial condition, we will just simply substitute the pressure at the initial condition, Z at the initial condition, and the temperature of the reservoir, and this is how we get the BGI in this case, initial. BG at any step in time, it will, for example, if we want to see the reserve of any reservoir after, for example, 5 year of the of production, we will just see the value of the pressure at after 5 year or at that specific moment of time. We substitute the amount of the value of the pressure with the temperature and that's the value, and we will simply get BG at that specific moment of time. And for example, if we also want to calculate or to estimate the reserve at the abundant stage, which that reservoir is no longer able to produce hydrocarbon. So in this case, we will just find out the pressure value at the abundant, which will basically, or of course, will be very low, the temperature and the Z value at that specific time, and we will substitute in the equation, we will get BG. Let's, for example, we can call it BGA, formation volume factor of gas at the abundant stage. We substitute it here and we will get the gas in place at the abundance stage. For oil, for the equation for formation volume factor of oil, it starts from the same point, but the only difference is that it's a correlation between two, so it's not a straightforward calculation as for the gas. So and the final output of this correlation is 1.05 plus n multiplied by 0 by 0.05, and n or gas oil ratio is the number of hundreds of cubic feet of gas produced per barrel of oil. So how many hundreds of cubic feet of gas it will be produced with every barrel of oil. So if we have, for example, we produce 1,000 cubic feet of gas per barrel of oil, N in this case is equal to 10, because we will divide 1,000 by 100, we will get 10, and then we substitute 10 here, and so on. So as I said, that after we calculate the reserve, the estimating the reserve at different cases or different scenarios, we can use those values to find out some important parameters. For example, we can get the unit recovery, which is the amount of hydrocarbon which is have been produced. So, and at this case we will just substitute the amount of hydrocarbon in the reservoir, or the reserve in the reservoir at any specific time, which is any specific pressure, or which is the pressure related to that specific time, from the the oil initially in place, or the stock oil initially in place. So it's by common sense. We will just take how much hydrocarbon is there in the reservoir right now, which is this value, and we substitute it from the amount of hydrocarbon which was there in the reservoir in the beginning. So the difference between them is the amount of hydrocarbon that we have been taken, or the amount of hydrocarbon which has been produced. Now the ultimate recovery, which is the maximum amount of hydrocarbon that have been produced, and in this it's the same equation. The only difference is that here the oil in place is calculated at the abandonment, which is the last production stage, or the last possible time for production, or the last possible pressure for production. So when we reach this stage, the abandonment, we are no longer able to produce from this reservoir. So we want to know how much hydrocarbon we have get from this reservoir, and it's simply we will calculate how we will estimate the reserve, the amount of hydrocarbon which we expected that it's still in the reservoir at this moment, which is the moment of the abandonment, and we take it from the initial oil in place, the amount of oil which was estimated as the beginning before the production. Now if we want to calculate the recovery factor, we simply calculate the amount of hydrocarbon that have been produced and divided by the amount of hydrocarbon which was there in the reservoir before production. So it's the ratio of the amount of hydrocarbon that has been produced to the initial amount of hydrocarbon which was there in the reservoir. So it will always be less than 100. It should be a ratio. So we can, for example, maybe we have taken 50%, we have taken 40%, so on. And as we said before, that most of the time the maximum recovery from hydrocarbon can be reached is 40% to 50% maximum in the best scenarios. And the recoverable hydrocarbon or the recoverable oil reserve is basically the oil originally oil in place or stock oil initially in place multiplied by the recovery factor. So this is the amount which is in this scenario I have estimated the amount of hydrocarbon in the reservoir, and I want to know how much of this hydrocarbon I can get. So we basically just multiply the recovery factor, which is the amount of hydrocarbon which has been produced so far, by the amount of hydrocarbon which have been already in the reservoir. Now we have some random definitions to go through. We have the reserve, which is the amount of hydrocarbon or the petroleum which is commercially to produce at this specific moment with the available technology. And when we say commercially, we are talking about quantity and in terms of quantity of hydrocarbon and even the price in this case, because if the price is low, that's meaning that means maybe even if you have high reserve but the price is low, maybe it will not be commercial. And if the amount of hydrocarbon also is not, or the reserve is not that much, so it will also be can be uncommercial. So the reserve has to be commercial to be considered as reserve. Reserve estimation is the process of estimate the amount of recoverable hydrocarbon in the field. And there is always uncertainty in the reserve estimation, and this uncertainty can be reduced by increasing the amount of data and quality of this data which is being used in reserve estimation. The recovery factor, which is the ratio, as we said, the ratio of the reserve producible amount to the total amount of hydrocarbon, of the total amount of oil or gas in a particular reservoir. So the amount that we can produce to the total amount which has already been there. The resource is equal to reserve, which is the amount which can be produced, and also the amount which cannot be produced by the current technology, or even cannot be recoverable by the current technology, even the discovered potential reservoir. So if we say that this country have this amount of resources, so we basically talking about the ones which is already there, the ones which is means the one which can be produced, and the ones which can not be produced by today's technology, and even the ones which are not being discovered yet. The reserves have different types. There is a proved or developed or producing reserve, and this one, which is it's already recovered and it's currently producing. So there is no doubt that there is hydrocarbon in this specific reservoir. And probable reservoir, which is between, it's less than the proved, because it's still maybe under study. There is no sufficient data, so there is around 50% uncertainty about the levels of recovery, and it's called P50 or 2P. And for a hydrocarbon reservoir, it can be, for example, a probable reservoir can be transformed into proved or developed if we collect more data and it has been developed and start producing. So that will shift it from probable to developed. So probable reservoirs are normally those ones which are under study, and we're still collecting data about them and so on. The possible reservoirs are those which have high uncertainty or 10% probability that the quantity of those hydrocarbons recovered will be estimated proved plus probable plus possible reserve can equal or exceed the sum of the estimated proved plus probable plus possible reserve. So we see that the probability is very low. We have only 10% probability that it can be proved or probable or possible. From seismic, this is how we can get the area in the equation of reserve estimation, because the output of the seismic is the seismic map, and from the seismic map we can get the area of our reservoir, and from the well logs we can get H, which is the thickness of our pay zone. Even from the seismic itself we can get an idea about the thickness, but again the transformation of the seismic to depth, we can rely on the well log as a depth provider. This is a summary for the response of different log with different lithology. It can be very helpful in carrying out the quick look evaluation. So if we have a sandstone that is compacted and dry, we will expect, of course, since it's sandstone, that the gamma ray will vary less because it have very low clay mineral, and since it's dry and compacted, so there is no fluid in there, we're expecting a very high resistivity, which is almost 1000. The porosity will be less than 10%, no fluid, no hydrogen, since it's compacted. The density will be more than 2.6, so because it's compacted. So we can see that the lithology and nature of this lithology in terms of its dry or compact, it can affect. If we can see here, same sandstone, but it's less compacted and wet. Of course, the gamma ray will not change because the lithology is sandstone, but you can see the difference that fluid can make in the resistivity, because the resistivity, as we said, it depends on the type of the fluid in the reservoir. So if it's unconducted, like if it's dry or it's contain unconducted fluid, we're expecting a high resistivity values. But here, since it's wet, we see that it's almost less than 100 if it's salt water, because it will be conducted, so the resistivity will be low. Porosity, since it's less compact, we're expecting 10 to 30% porosity. It might also have hydrogen if it's containing hydrocarbons, so it will have hydrogen, and we're expecting that the neutron, of course, would respond to that. The density difference here, because it was compacted, it gives us 2.6, while here, since it's less compacted, it will be 2.9, and so on. So those are different scenarios or different lithologies, and it will be very helpful for the quick look evaluation and identification of different lithology. Of course, the knowledge comes with experience, but as a beginning, we can rely on such generalizations in order to develop a general idea. So I guess this was the last slide. Thank you.